Okay, guys. So in the previous lecture, we started introducing magnetism. The basic ideas of magnetism, right? And we discussed that if a charge, positive or negative, it doesn't matter. If a charge moves, then the charge produces a completely new field, new to the electric field, right? So that new field is called the magnetic field, right? So let me write. So first we are going to discuss what is called magnetism. Magnetism, right? And as I said, the basic idea, if you have a charge Q which moves with velocity v, then this charge produces magnetic field. We're going to use the symbol B to denote magnetic field. Then, if a charge is capable of producing magnetic field, then if you have a bunch of charges moving in the same direction, then of course they are going to produce magnetic field. Bunch of charges moving in the same direction, that is the current. So the second system which we're going to discuss, if you have a current, right, let's say flows in a certain direction, then this current produces magnetic field also. In the last system which we're going to discuss from time to time, a permanent magnet. So if you have permanent magnet, let's say North Pole, South Pole, then of course this system produces also magnetic field. Okay, so these systems are capable of producing the magnetic field. Now, the next question, what can be used to detect magnetic field, to probe magnetic field, right? And we discussed in the class, so the probe system to detect magnetic field is, we are going to use a compass needle. A compass needle. It's basically a small magnet, right? So let me write, so the probe system, a compass needle. Right? And if I draw, for example, this is the compass needle, right? Usually one side, we usually show it is with red. It's a North Pole. We discussed why one of the sides is called the North Pole and the other one is the South. And so if you use compass needle to probe magnetic field, then direction of the North Pole shows us direction of the magnetic field. So if the North Pole of the needle shows that way, so that's the direction of the magnetic field. If the compass needle shows that way, North Pole of the compass needle shows that way, direction, that's the direction of the magnetic field. Okay, then what's next? So let's imagine that we have a permanent magnet. Right, North Pole, South Pole. And so now you can use this compass needle to map the magnetic field, like you mapped electric field using a small positive probe charge in your lab number 1. Now we can use the compass needle to map magnetic field. Let's assume that you mapped it, and you will find that magnetic fields in this case will look like this, right? And it looks like they start from the North Pole, it looks like, and end on the South Pole. Why I keep saying it looks like? Because there is a very interesting feature of the magnetic field lines. Since there are no magnetic monopoles, so far in the nature no one has found magnetic monopoles. Since there are no magnetic monopoles, as a consequence, magnetic field lines form closed loops all the time. It doesn't matter how complicated your magnetic field is. If you find properly magnetic field lines, all the time they must form closed loops, period. They must be closed. So that's why I said it looks like they are getting out of the North Pole and enters into the South Pole, because inside of the magnet, these magnetic field lines gets closed. This magnetic field line gets closed inside of this permanent magnet, right? So every time magnetic field lines are closed loops. I can draw something like this here, right? Then I can do this, right? Here also something similar, right? Wrong direction. Right. Okay, and maybe extra this way to make it look better. Right. So these are magnetic field lines. So we use them to visualize magnetic field, because again, magnetic field is invisible. And the ideas behind magnetic field lines are very similar to the ideas which we used to visualize electric field, using electric field lines. So now let's assume that of course I need to close these magnetic field lines, right? So they're all closed. Now let's assume that somebody gives you this magnetic field lines. So how can you extract information about the magnetic field? Because these are magnetic field lines. How can we extract information about the magnetic field? Let's say at let's say, for example, at this point. Yeah, at this point. So we want to find the magnetic field. So magnetic field all the time is tangent to the magnetic field lines, B, right? And so direction is tangent. Okay, let me write over here. Direction, tangent. And what about the strength? Magnetic field strength. Magnetic field strength in the density of lines. If density of lines over here, since density of lines over here is larger, so the magnetic field is stronger. Here density of lines is smaller, so the magnetic field is weaker. All right, so we can write in density of lines, right? So if I draw it here, let's say this is the battery. This is the magnetic field. All right, and if we look over here at this point, for example, at this point, so magnetic field is going to be stronger, right? If I draw it here, magnetic field will be represented by this vector. Okay, so now you can get information about the electric field strength and electric field direction from the magnetic field lines. Okay, so now next, let's look at this system. Moving charge, positive or negative, it doesn't matter. Let me separate this, something like this, right? And now let's introduce Biot-Savart Law. Biot-Savart Law describes magnetic field produced by moving charge and by a wire with current. So let's first look at this system. And I will write Biot-Savart Law for a point charge Q, right? Again, this is the fundamental law, which cannot be derived. So what we can do, we can just present it and discuss it. That's it, right? So how it was written, a bunch of data, right? And then people tried to come up with the expression which would explain that set of data. Okay, so let's start with the picture. So let's assume that we have a charge Q. Let's assume it travels this way. So this is velocity v. And let's assume that we want to find magnetic field at this point P. Completely arbitrary point somewhere in space. Let's assume that the distance to that point is r, right? Small r. Then we will need, since I'm going to write this law in a vector form. So in order to do that, we will have to introduce a unit vector r hat, which shows direction, which shows a direction to the point in question. So let me introduce this vector r hat, unit vector. Absolute value of that vector is 1 by definition. You don't have to think every time by definition. The absolute value of the vectors like this is 1, r hat. And I guess that's it. So now we can start writing down the Biot-Savart law. So magnetic field at this point equals mu naught, new constant, which we're going to discuss in a second, divided by 4 pi times the value of the charge. It can be positive, it can be negative. It depends on the charge. Then cross product or vector product of the velocity vector and our unit vector r hat, and divided by r squared. So that's the Biot-Savart law for a point charge. Okay, I can frame it. Right, and now let's discuss. First of all, constant mu naught. Okay, first let me write the value. 4 pi times 10 to the power of minus 7 units of magnetic field. Units of magnetic field are Tesla. Tesla, named after that great guy who did lots of he introduced lots of innovations at the beginning of 20th century, right? So Tesla. Right. And so now I can write units of mu naught, which is actually called permeability of free space, permeability constant. So Tesla meters divided by m. Okay, that is permeability. Permeability constant. Permeability constant. So now, what's next can be discussed. Direction. Direction, B is the vector, right, at this point. So what determines a direction? Direction is in this cross product, V cross R. In this case, V, let's find direction. V that way, R is that way. So if I take a cross product using a right-hand rule, V cross R, and my outstretched thumb gives me direction of the magnetic field that way. It looks like that way, right? So now, so this determines direction. Let me write this way. So direction. All right. V cross R. It looks like this determines direction, but that is not the whole story. Why it's not the whole story? Because we have charge in front. And this charge can be positive and negative. If our charge is positive, let's say, for example, it's a proton, then yes, direction of V cross R is going to give us direction of the magnetic field. Like if this is positive charge, then direction of the magnetic field is going to be towards you, out of the board. But if charge is negative, then whatever direction you find here, you have to flip it. That minus in front of this charge is going to flip direction of your direction which you find in this cross product, right? So be careful with sign of the charge, right? So that's why I put this figure bracket, and this determines, right? So this can be positive or negative, right? So these two elements in this formula determines direction of the magnetic field at point P. Again, in this particular case, if charge is positive, direction of the magnetic field will be towards you. If charge is negative, direction of the magnetic field at this point P will be into the board. Right, so let me check what else I should say to make sure that I didn't forget anything. Yeah, mu naught. I wrote it down, the value of mu naught. Physical meaning. I think of this constant, permeability constant, as a constant which describes magnetic property of a vacuum. Magnetic property of a vacuum. Idea is very similar to epsilon naught. You remember constant in electricity. If this space were filled with some material, not a vacuum, then here we would have a different constant mu, not just mu naught. So mu naught is a property of a vacuum, magnetic property of a vacuum. If this were filled with some material, constant mu naught we would have to replace with some mu. Now, okay, the last formula, no, two more formulas. I will probably move up here. Now, so we wrote down Biot-Savart law for charge. Now let's write Biot-Savart law for a current. Biot-Savart law for a current. Okay, it's basically the same law. It's basically the same law, but written for different systems. You can easily make a transition from this formula to what I'm going to write, or in the opposite direction. If you know this formula, you should be able to make a transition to this one easily. We're not going to make this transition. We're going to logically rewrite this formula into the new form. So, mu naught over 4 pi, we cannot change that. All right, so we have to replace charge in this formula logically with current, right? So charge here, current there, right? So basically now we want to write expression for the magnetic field created by a current. So if you replace in this formula charge with current, that's the first transition, step in the transition, first step in the transition. Then V. Now we have a bunch of charges, not just one charge, and we have to replace it with, okay, you know what? Before I write, before I start writing this, I need to draw the picture. Now I realized that I should have started with the picture. Let's assume that we have a piece of wire, right? It can be straight, it can be curved, it can be bent, any piece of wire with current. So let's assume that we have a current I flows that way, and this is piece of wire. So let's assume that we want to find, for example, magnetic field at this point P, right? So what we have to do, we have to take infinitesimally small segment of this current, let's call it ds, right? Infinitesimally small. It means it's smaller than any length you can think of, right? And you see I wrote ds as a vector on purpose. What determines direction of this vector ds? Current. If current that way, ds is that way. If current flows this way, direction of ds also that way. Direction of ds is determined by the current. So now I'm ready to write the factor which I have to use to rewrite this formula. Instead of v, I have to use this ds. ds. Right, and the rest is exactly the same. So again, just charge with current, and instead of V, ds. The rest of the formula is exactly the same. So now let me just draw again. This is R, this is unit vector R hat, and now I'm ready to rewrite a Biot-Savart law for a current. dB equals the same constant mu naught, permeability of free space, permeability constant, divided by 4 pi, And again, 4 pi was introduced just for the sake of convenience, because you see how we introduce mu naught 4 pi, so that this 4 pi and this 4 pi can be easily cancelled. Then, instead of charge, we have I. Instead of V, we have ds crossed with a unit vector. Again, this is just a unit vector r hat, so absolute value is 1. Because I see every time on the exam, almost every semester, quite a few students struggling, try to find the value of r hat. The value of r hat is just 1. Then, and divided by r squared. Okay, so now I'm ready to frame it. So that's Biot-Savart law for a current. Okay, so now next, oh, maybe you know what I should write to show that ds direction, it's a direction of current, direction of ds, direction of current. Let me write that down, because some students tend to forget this. So I think this is enough. And now the last formula which I need to introduce. This formula can be used for any piece of wire, straight, bend, curved, twisted. You can apply it for any current. Of course, integration can be very, very difficult, right? Even for an infinitely long straight wire with current, even for that system, finding magnetic field is quite complicated, right? I did once in my first semester. I went through that integration, right? So we're going to write in a second, it was kind of shocking for students. So after that, I don't derive the formula which I'm going to write. Again, now I want to write the formula for the magnetic field created by an infinitely long straight wire. So what do you have to do? You just need to take this formula, Biot-Savart law for a current, and integrate it from that side of the wire with current to that side, which is basically infinitely long. So from that infinity to that infinity, right? So if you do it, as I said, I'm not going to do this integration, because next class, most likely, we were going to derive this formula easily using Ampere's law. So I decided it's not worth of struggling if in the class we will be able to derive that formula much, much easier, right? Okay, so now let me write something like this. Okay, if we apply this formula for an infinitely long, right? So it's the sign of infinity, infinitely long wire with current. In this case, current is constant in time, right? Current is constant in time. Then we can, if we apply, we can derive. Right. Probably first I will draw the picture. So this is our infinitely long straight wire. Okay, you know what? I should add straight over here. Infinitely long straight wire with current I. It's very important, right? So the wire is straight. So like this. And so if there is a current I flowing through this wire, let's say that way, then of course this wire produces magnetic field, right? And now we can derive the formula. So I will just write the formula. B equals mu naught, our newly introduced constant, times the value of the current, and divided by 2 pi. In this case we used R or D? D. Okay. 2 pi D. What is D? Here you need to know what does D mean. So let's say you want to find magnetic field at this point P. So D is distance from the center of the wire to the place where you want to find the magnetic field. So that's what D is. It's a perpendicular, or the shortest distance from the center of the wire to the point where you want to find the magnetic field. Okay, so that is the formula which we're going to use a lot, and usually students don't have troubles with applying and understanding this formula. Now, it's an absolute value. This is the absolute value, magnitude of the magnetic field. What about direction? Direction, magnetic field lines form circles. So if you have wire, so let's assume that this is the wire, right? So magnetic field lines are circles, all right? Concentric circles, right? And direction, how can we find direction of those magnetic field lines? We will use right hand rule. Usually I call it number 2. Right hand rule number 1, it's the rule which we use to find direction of the cross product. Right hand rule number 2, that's what we're going to use to find a direction of the magnetic field lines in this case. So what you have to do, let's assume current flows that way in this wire. So what you do, you outstretch your thumb of your right hand in the direction of the current, and then your curled fingers gives you direction of the magnetic field, direction of the magnetic field lines. Right. It's a very simple rule. Usually, again, students don't have much troubles with this right-hand rule. Students have much more troubles over here. In this right-hand rule, not much. Okay, so now let me try to draw these magnetic field lines. So, direction of the current that way, and then magnetic field lines above the wire will be towards us, out of the board, and below will be into the board. So it will be something like this, right? Let me draw. Right, you see here, this magnetic field line is behind the wire. So, and direction, this. Right. So now I can draw the second. Right. Again, below magnetic field is into the board. Above this wire is out of the board. So I'm just trying to draw a three-dimensional picture. So these are magnetic field lines, right? And that is the absolute value of this magnetic field. Okay, so we're going to use this formula we're going to use next class in one problem, right? Because this formula, of course, requires every time an integration, and in that problem, integration is not going to be difficult. Here, it usually doesn't require any integration, right? So you just apply the formula for 1 or 2 or 3 wires, infinitely long straight wires. And of course, this formula we're going to use today, actually now, to find magnetic field produced by a point charge, right? Okay, I think I've mentioned everything which I was planning to mention, and now let's look at the examples. Okay, all right, so now let's look at example. Let me erase this part, which I don't think I will need. And let's look at this example. We have some point charge, actually positive point charge, a proton, right? So which flies with a certain speed, constant speed. And let's look at this charge at a particular moment of time, sort of mentally freeze it. And now I'm going to draw that picture. And that is a problem 29.6. Problem 29.6. So that's the problem. So what we have? We have a flying proton. So we have a proton which moves with velocity, 2 times 10 to the power of 7 meters per second. And then some geometry is given, but I need to draw the picture in order to give you that geometry. And I will start drawing a picture with a picture of a coordinate system. Let me estimate how much of space I might need. Right, I guess I will do. I can do better. Right, so let's see. So this is my y-axis. This is my x-axis, right? Z-axis, let's use a right-handed coordinate system. Z-axis will be out of the board. So this will be z-axis. You remember the convention about these directions. So if out of the board, it means we use a dot, right? Cross, it means into the board. Then our proton. So let's assume at this particular moment of time t, the proton is over here. So that's our charge q, which flies this way. So v, right? And let's assume that our velocity I already wrote down, right? And so we have a charge which moves. It means that it produces magnetic field. Of course, it produces magnetic field everywhere. So the question says, find the magnetic field at a point over here. So point P. So we need to find magnetic field at that point. So what do we know about that point? We know that this distance is A. And this distance is B. It's just at this particular moment of time. Of course, the next moment of time, the charge will get closer, right, to this point. So B will start going down and so on, right? So, but at this particular moment of time, this distance is A, this distance is B, and these distances are equal. For the sake of simplicity, actually it's, what's the 1 centimeter. Okay, let me convert to meters, right? 1 times 10 to the power of minus 2 meters. M small meters. Right? So we need to find magnetic field at point P. So find B at point P. So it means we need to find direction of the magnetic field and its strength. Right? Because again, magnetic field is a vector, so we need to find both parts. Okay, so what? Physics is quite straightforward. Physics is quite simple. We have a charge which moves, it produces magnetic field. We know the formula, Biot-Savart Law, which describes magnetic field. So we just need to grab that formula and apply it in our problem. So not much of a discussion. So now we just need to properly apply this formula. Look at the cross product, look at all these parameters, right? So probably first I will just rewrite the formula. It's a good habit of when you solve the problem, write formula or formulas which you're going to use. So B equals permeability divided by 4 pi times charge, cross product of the velocity and the unit vector r hat divided by square of the distance from r, it's a distance from the charge to the point where you want to find magnetic field. You see this picture? R, it's not from the origin. Origin can be somewhere else, right? But in this formula, R, it's a distance from the charge to the point where you want to find the magnetic field, right? So you just need to remember all this. Right? So in this case, you see the origin is at this point, but this r, it's a distance from the charge, from our proton to the point where we want to find magnetic field. So let me draw it. So that is our r, and of course r hat is just a vector showing that direction. Okay, let me use different color. All right. No. Let me use black. Yeah, black. So this is r hat, right? So that is r hat. So this, okay, so all the vectors which we need are on the picture. So now we should be able to, now we can start actually getting the solution. So let me frame it. Right. And you know what? I will probably start first with direction. I will start with the direction of B. Direction. Again, you remember direction. What determines the direction? The cross product of V and R hat and the sign of the charge. So in this case, V cross R, V cross R, V that way. So now we have to apply right-hand rule number 1, right? So over here we had right-hand rule number 2. Now it's right-hand rule number 1, which we use to find direction of the cross product. Okay, so first vector in the cross product. So V that way. Then cross it with R hat. Okay, so right-hand rule. First, you position your hand along the direction of the first vector in the cross product, along V, that way. Then you need to orient your hand in such a way so that you can bend your fingers, these fingers, in the direction of vector R. Vector R points that way. So I have to orient my hand like this. V cross R gives me direction of the magnetic field. In this case, you see my thumb points into the board. So V cross R is direction, give us direction into the board, which is minus Z direction. You see, Z direction is out of the board, but our V cross R is into the board. So it gives us minus Z hat direction. Or you can use K hat, right? Then, of course, next step, we have to check the sign of Q. Our Q is positive because we have a proton. Okay, the proton. So Q is positive, so no troubles from the sign. So in this case, direction of V cross R determines direction of the magnetic field. So out of this, we can say that magnetic field is in the Z direction, absolute value in minus Z hat direction, right? B times, in the brackets, minus Z hat. Okay, actually I can write it here, right, and then I will continue. So absolute value of B times minus Z hat direction. Okay, so now we just need to find absolute value. So I will continue over here. You know what? Before, let me. I will probably write what is R squared. R, it's this, right? Obviously, you can see how we can find the value of R. Pythagorean theorem, you see this triangle, it's a right triangle, so R squared equals to A squared plus B squared, right? So let me write it over here. R squared equals to A squared plus B squared. And the rest I will write over here below. So B equals, let me write down direction immediately. And now the rest will give us our absolute value of the strength of the magnetic field. Mu naught over 4 pi, no troubles. So we just need to rewrite that. Then charge Q. Again, I will just rewrite Q. Now, absolute value of V cross R. Absolute value of V cross R. You remember the absolute value of the cross product. It's absolute value of the first vector, V. Then, absolute value of the second vector in the cross product, R hat. And then sine of angle between them, right? Sine of angle between V and R. Sine, which angle? Okay, actually, in this case, picture is very nice. It gives us the correct angle immediately, right? You remember how can we find the angle between two vectors? You need to position their tails at the same point. Tail of V and tail of R. And that's what we have. Tail of R hat and tail of V are at the same point. So this is the correct angle. So let me call it theta, right? Okay, so sine of theta and divided by R okay, you know what? Let me write immediately a squared and b squared. A squared plus b squared. Okay, and at this point, I've seen, okay, not many, but quite a few students struggle. At this point, they start finding absolute value of r hat. You don't have to find it. We know by definition absolute value of r is 1. All right, okay, so, and now let me open the explanation box in order to find angle theta. Okay, again, this right triangle, tangent of this angle theta equals to A versus B, opposite versus adjacent side, right? Properties of a right triangle. Tangent of theta equals to opposite A versus B. And since A and B are equal, so theta is 45 degrees. Right, so theta equals to 45 degrees. Okay, and now I can actually plug numbers, right? And we can calculate it through. All right, so minus z hat direction, then mu naught, it's a 4 pi times 10 to the power of minus 7 Tesla times meters over amperes divided by 4 pi, and you see 4 pi gets cancelled immediately, right? Charge of the proton equals to the charge of an electron, but positive. So it's just 1.6 times 10 to the power of minus 19 coulombs. Then velocity is already in meters, 2 times 10 to the power of 7 meters per second. Sine of 40, this is just 1, right? R hat, absolute value of R hat is just 1, and sine of 45 degrees, and divided by a squared plus b squared. So a and b are the same, so it's a 1 times 10 to the power of minus 2 meters squared plus 1 times 10 to the power of minus 2 meters squared, right? Okay, so you can multiply all these factors, which I'm not going to do. You will end up with 1.13 times 10 to the power minus 15 units of Tesla. Direction, okay, I will put a small multiplication, minus z hat direction, right? Absolute value and direction. So that's how you can use this Biot-Savart law to find magnetic field produced by a moving point charge. Again, you see, I told you at the very beginning, magnetic field is produced only by moving charges. Every time, velocity must be involved. It's sort of dynamics, right? So velocity must be involved. Right, and so the troubles in this problem, usually in opening this V cross R, finding the correct direction, and then, in this problem, yeah, V cross R, finding this direction, and of course, in finding the absolute value of the unit vector. All right, every time I'm kind of surprised, but quite a few students struggle at this point. Absolute value of any unit vector, by definition, is 1. That's how we introduce those unit vectors. So you don't have to think at this point. Right, so that's the problem 6, chapter 29. And now, let me move this over here. Let's look at the second example. And now we're going to play with this formula. We're going to use this formula next recitation class, right? So let me separate it like this, right? Or maybe with two lines, right? Big separation. In the problem 14, part A, in your homework, you're going to have the whole problem, right? 14, part A, B, and C, right? So we're going to discuss only part A. because the rest will be very similar, idea will be similar, just slightly different configuration. So what do we have? We have two infinitely long straight wires, and they parallel to each other. So we have a wire with current, and current will be flowing that way. The second wire parallel to the first one, but current will be flowing in the opposite direction, right? And we will have to find the magnetic field at a certain point. Okay, let me start with the picture. And you know what? Let me erase this. Right. So the first one, okay, I will use different colors for wires. So let's assume the first one will be the blue. Right. And current flows that way. So that is wire number 1, and current flows that way. Absolute value of the current, exactly the same. Right. So that's the first one. Second, okay, I will use green. The second one is over here. Right. And current flows in the opposite direction. So two wires, infinitely long wires, straight wires with current. And what the value of I is 10 amps, so quite a current, 10 amps of current. Then physics is very simple, right? So this wire creates a magnetic field everywhere, so the whole space is filled with the magnetic field produced by the wire 1. Then the same space is filled with a magnetic field produced by the wire 2. So if you want to find the net magnetic field at any point, so of course you will have to apply principle of superposition in order to find the net magnetic field. So we will, in this part A, we will find magnetic field at some point above, over here. In your homework, you will have to also find magnetic field between the wires and below, right? So this will be part A, part B, and part C. So what do we know about point in part A? Right, that point is at the distance D from the upper wire, right? So you see, from the upper wire, distance D. The value of D is 2 centimeters. Okay, let me convert to meters immediately. 2 times 10 to the power of minus 2 meters. Then, also, we know the distance between these two wires. So that is given using symbol L. And the value of L is 4 centimeters. So it's a 4 times 10 to the power of minus 2 meters. So that's what is given. And we need to find magnetic field at that point. Let me call it, I don't know, P. At this point, P. Right, so we need to find magnetic field at that point P. So this is P. Okay, it looks like D. Let me P. Right. Okay. Okay, I still have enough room, and then I will probably move to that side. Very simple. Principle of superposition. So first we need to find magnetic field at this point P created by the first wire, direction, strength, and then we have to do the same for the wire 2. We will have to find magnetic field strength and direction at this point P, and then we will have to add those two vectors. And again, don't forget that magnetic field is a vector, so you have to keep track of directions, right? So let me write. So first in general, so B, this is the net magnetic field at point P. Of course it will be B1 plus B2, right? So you see, I wrote them as vectors. So now let's find direction of B1 and direction of B2 at this point. So it's an application of this formula. And the right-hand rule number 2. Maybe you know what I should have written. So how can we find direction? Right-hand rule number 2. Right. Okay. So let's start with the first wire. first wire, it's exactly the same picture as over here, right? So current is the same, direction of the current the same. So in order to find direction of the magnetic field, outstretch your thumb in the direction of the current, and then curl your fingers around the wire. So the wire must be so you have to sort of like a circle the wire with your fingers, right? Okay, so if you do that, you see magnetic field, direction of the magnetic field above the wire is towards us, right? Below, into the board. Right? So magnetic field lines are going to be like this. I will use blue color. All right, so something like this. So this, right? And also I can draw another. All right, so this. Again, so I'm trying to draw a three-dimensional picture. So those magnetic field lines, these parts of the magnetic field lines are below the wire, so that's why they're not visible, and these are in front, right? You can easily, you should be able to imagine that easily. Right, so it looks like B1 at point P, so since point P is above the wire 1, so it is out of the board. So B1 is out of the board. That's a dot. That is a dot. So B1, right? So direction of the magnetic field B1 at point P, out of the board. Now green, exactly the same story, but now the current flows that way. So in order to apply right-hand rule, so outstretch your thumb in this direction, in that direction, and curl your fingers around the wire. So it means that magnetic field lines will have this structure. So this, right? And this will be in, right? So opposite direction to that direction, right? Okay, and of course, if you draw magnetic field line which is over here, right? So you will have something like this, right? And the magnetic field line points into the board, into the screen, right? So it means that at point P, magnetic field, we have to use the cross, right? So B2 is into the board, into the whiteboard. Right, so they are in opposite directions. You know what? In order to use vector notations, let me also introduce coordinate systems. So let me introduce these coordinates. Let me follow mine. Okay, so let's say X that way, Y up, and then we're going to use the right-handed coordinate system, X cross Y. So Z-axis will be out of the board. So let me introduce, again, you can introduce different coordinate system. I decided to introduce this coordinate system, so Z-axis is out of the board, right, out of the board. And so now I'm going to write our magnetic field vectors in terms of Z direction, right, because everything is happening here in Z direction. So I can write, so B1 is in the direction, in Z direction, is in the Z direction. You see Z is out, magnetic field B1 is also out. And absolute value of the magnetic field is here, given by this formula, mu naught I divided by 2 pi, and the perpendicular distance from the center of the wire to the point where you want to find the magnetic field. Okay, so now we've made all the preliminary steps. Now we should be able to write this, continue writing this line. So B1, mu naught I divided by 2 pi. Which distance do we have to use for B1? This distance from the wire 1 to the point where we want to find the magnetic field, to the point in question, which is D. D. All right. Direction. B1 is in the Z direction, so I will write in the positive Z direction. So that's contribution to the net magnetic field at point P. Contribution from the first wire. Now let's find contribution from the second wire. The same formula, right? Mu naught times I. Again, currents are the same. Absolute value of the currents are the same. This and this, both 10 amps. So as a result, here the same I and here the same I. 2 pi. And now D. What is D for wire 2? Again, it's D, it's a distance from the wire to the point in question. In this case, from the wire 2 to the point P. So that distance is L plus D. So here I have to write L plus D. L plus D. And direction. Direction B2 cross, which is into the board, opposite to the chosen Z direction. Again, I decided to use this Z direction. Right. So this is opposite to my chosen Z direction, positive Z direction. So minus Z hat. Right. Or you can use K hat. Right. So what's left? Now we just need to calculate. Everything is given. Mu naught we know. Where is mu naught? Here. Current is given. Distances are given. I converted them into meters already, no troubles. And so now Z can be factored out. Some other things can be factored out. Let me make it look nicer, and then I will write the numerical answer. So mu naught I. You know what? Let me start with direction. Z hat, then mu naught I divided by 2 pi. So I factored out common factors, right? Right, mu naught I, 2 pi, Z, and so what's left inside? Inside 1 over D minus 1 over L plus D. 1 over D minus 1 over L plus D. Right, again, these are 1 and 1. This is L. Okay, so, and after calculating through these parameters, right, after multiplying, dividing, okay, you will end up with 6.7 times 10 to the power of minus 5 Tesla, and direction of the magnetic field is in the Z direction. Okay, it should be enough for today. All right, so out of these three formulas we used today Biot-Savart Law for point charge. Then we used this formula for magnetic field produced by an infinitely long straight wire, and this formula we're going to use it next class, right? So it will require some integration, so it's a little bit more challenging from the mathematical point of view, but we will look at the system, which is nice and symmetrical, right? So it's not going to be that bad, all right? And then maybe in my lecture, I will look at the example when these two wires are sort of perpendicular to each other. If we take this wire, like for example, number 1, and turn it by 90 degrees so that it points into the board. So this wire is still this way, but the second is perpendicular. So we'll have to find the magnetic field somewhere between them, right? Okay, enough. And then I'll see you next time.